So, hi everyone. I usually start by saying good morning, but now, I guess we have to give up good morning. It's good afternoon, good night, good evening to everyone. Welcome to our 17th CRM camp seminar. And today it's my pleasure to have Kevin Church from McGill University. He's a postdoc, an NSERC postdoc at McGill, and he started a year ago. And Kevin received his master from University of Ottawa in 2014. He got his Ph.D. in 2019 from University of Waterloo in Ontario under the supervision of Xinzhi. And his work during his PhD was on invariant manifold theory for impulsive functional delay differential equation. And since he joined McGill, so he's been working on still on impulsive delay differential equations, and he started slowly to do the rigorous numerics. And I guess this is what he's going to be talking about today. So please, Kevin, it's all yours.
Great. Thank you, Jean-Philippe, for the introduction, and thank you for the organizers for hosting these seminars. It's been great having something to look forward to every Tuesday. Let me just share my screen and get my presentation up here. A moment. Okay. So. So I'm going to be talking today about rigorous computation of periodic solutions and also Floquet multipliers in delay differential equations with, I say, time-forced discontinuities. But as was suggested by Jean-Philippe, I'm mostly going to be talking about impulsive delay differential equations. So I'll give a little bit of background on this before moving to sort of the first half of the talk, which is on a way to rigorously compute periodic solutions in these types of systems. This part is with some joint work that I'm doing with Gabriel Duchesne, also at McGill. After that part, I'll move on to sort of the second half, which is about stability, Floquet multipliers for periodic solutions, and how to rigorously compute those. And then I'll do an application, which is the pulse harvested Hutchinson equation. So some background on impulsive delay DEs, if you do not know what these are. Basically, it's the combination of a delay differential equation and sometimes called a reset map, sometimes called a jump map. Basically, an additional constraint that says at certain times, the solution jumps discontinuously from one state to the next. And there is some kind of, there's some sort of function. In this case, I've written it as G that applies this operation. And there's a bit of common notation that's typically used here. We use this simple delta X to denote the difference or the sort of size of the jump. It's quantified in terms of a difference between a function at a specific time and the left limit. And we can do this in a more general situation for a general functional differential equation, but here we're just focusing on a single discrete delay, as that is, one of the simplest cases we can do. So if you want to look at, what these solutions look like, or just a simple example, at the bottom I have a fairly basic delay differential equation, and I've appended this jump condition that says when the times are integers, the state changes by an amount that is a fixed amount, and it's just rho. So you have a couple of plots of solutions that you can see down there at the very bottom. In particular, it looks like we have a periodic solution when rho is equal to -1 and -2. Looks like there's a period doubling bifurcation happening somewhere between -2 and -5/2. And one thing that I have not talked about here is, for example, you can prove that when rho is equal to 0, there is a saddle node bifurcation of periodic solutions. And this brings me to the sort of main point or the main difference between impulsive DEs or impulsive delay DEs and delay differential equations without impulses or without any kind of like forcing added, which is that you typically don't have fixed points. If you do have fixed points, they don't persist if you perturb your vector field or your jump function a little bit, because these types of problems, that of finding a fixed point, are overdetermined. So you have too many equations, not enough variables. So what typically happens is if you want to talk about nice invariant sets, you need to just talk about, in the most general setting possible, hyperbolic bounded complete trajectories. but we can say a little bit more if, for example, the sequence of impulse times, these t subscript k's, are periodic. And if that's the case, then there's a Floquet theory. We could talk about Floquet multipliers. We can talk about stability, instability in a fairly nice, computationally appropriate way. And I'm going to be talking about a little bit about that later, actually. So that is that's the setup we're going to be looking at. We're primarily going to be focusing on this case where the sequence of impulse times, these tk, are periodic. So simplest situation is that they are just evenly spaced with some distance p from each other. So p is in some sense the fundamental period of my entire dynamical system. And what we can now do is, since we only have a discrete delay, we can basically rescale time and assume without loss of generality that the delay is equal to 1. This is just for just to make the presentation a little bit easier. So we can always do that in this case. And then we have two sort of propositions that will kind of guide what we do pretty much for this entire talk, which basically says that if I have a periodic solution and it has some specified period, then exactly one of two things has to happen. Either the period has to be a multiple of that fundamental period. That makes sense if you've looked at differential equations with some periodic forcing. The alternative is that very rare, the period is not a multiple of the fundamental period, and the function psi is continuous. So in some sense, your periodic solution is a periodic solution of the delay dE itself if you strip out the impulse effect. So it's kind of, in some sense, boring because it's just a periodic orbit in a delay dE. There are no discontinuities. The impulse effect does nothing. And then the other thing is that if the period is rational, then in some sense, the structure of the periodic solution is nice because it is piecewise analytic. Now, I haven't written a converse to this because if the period is irrational, then some very weird things can happen. It could very well be that the solution is still has some nice regularity properties, but what is going to be more typical is that it's actually going to be non-smooth on a dense subset of its domain. So it's a very, very bad situation, which for the remainder of the talk, I'm going to ignore and pretend is just not a problem. And I'm going to focus on this setting here, where I'm looking for periodic solutions, where the period is a multiple of the fundamental period, and where the period itself, the fundamental period, p, is a rational number. So at this point, I'm going to move on to this joint work with Gabriel, where I'm going to talk a little bit about how to represent and compute periodic solutions of these types of systems. So there's a little bit of natural motivation here. If you've seen the method of steps for delayed differential equations, this is sort of the starting point. I'll just refresh here how this works. We have an initial condition, which is specified on an entire time interval from -0 to 1, because our delayed differential equation has this delay of time 1. So we have to specify a large interval of initial conditions. And how the method of steps works is that we observe that, well, if t is between 0 and 1, then t minus 1 is between -1 and 0. And as a result, I can solve my delay dE on the interval 0 to 1 using the initial condition for the delayed part. So I've quantified that here by some use of colors and rewritten these differential equations in these various panes between 0 to 1 and 1 to 2. So once we've solved from 0 to 1, now we have to solve from 1 to 2, and we just play the same game over again. We can now solve our delayed differential equation on the interval 1 to 2 by just taking what we computed from 0 to 1 as our delayed part. So you get this sort of iterative process where solutions in one interval are chained to compute the solutions in the next ones. And of course, when we do these kinds of things rigorously, we have some pretty nice wrapping that goes on, but that's another topic. But we're not just interested in computing solutions from arbitrary initial conditions. We're actually interested in a very specific situation where we have a periodic solution. So I should emphasize right now, I'm just looking at delayed differential equations. I'm not talking about delayed differential equations with impulses. I'll deal with the jumps later. Right now, just everything is continuous. So for example, suppose my function x is periodic with period 3/2. So that means by definition, for every value of t, x at t minus 1 is equal to x at t plus 1/2. So what I can do is I can look at a couple of intervals and see, well, how could I solve this? So on the interval 0 to 1/2, I can write down my delayed differential equation. And since x at t minus 1 is equal to x at t plus 1/2, if I now look and see where t plus 1/2 is, it would be in the interval 1/2 to 1. So it's sort of one segment forward because my solution is periodic. So I can write down the derivative of that part of the solution between 0 and 1/2 in terms of itself and the segment that is 1/2 interval forward, or 1/2 time unit forward. I can do the exact same thing for the interval 1/2 to 1. And it's the exact same argument to do that. For the interval 1 to 3/2, I have to be a little bit careful because well, I don't have to be, but it's beneficial to not do that shift at to plus 1/2. We just leave t minus 1 as is, because if t is between 1 and 3/2, then t minus 1 is between 0 and 1/2. So now, in terms of this labeling that I've done here in the figure, this part of the solution, x subscript 1, its derivative is determined by itself and x subscript 0. So we have this sort of looping thing going around where each sort of segment of our periodic solution is determined by itself and the next one. And then we have a sort of, they kind of like wrap around when we get to the third one. So we can make this process a little bit nicer looking. We can define a little change of variables. So all this change of variables is doing is it is taking each of those solution pieces and mapping them down so that all of their domains are the same. Their domains are all 0 to 1/2. The 1/2 is coming from the denominator of the period in this case. Period was 3/2, so it makes sense to split it into 3 pieces, each of length 1/2. And if we do that, then basically each of these segments satisfies an ordinary differential equation. And then we have this additional boundary condition. The boundary condition here says 2 things. The solution is continuous. The continuity condition is basically the first 2 of these. And the last one is the periodicity. So by specifying that the last segment at its right endpoint is equal to the first, or in this case, 0th segment at its left endpoint, you're basically enforcing periodicity to this representation of the function. So basically these, what I'm calling solution segments, these z sub k's, they're cyclically chained to each other by ODEs and boundary conditions. And this setup works in general. This is a somewhat ugly technical slide, but the main point is that if the period is, again, some rational number, and I express it in its lowest forms as P1 over P2, where these P1 and P2 are coprime, then any periodic solution that is with a period multiple of that can be split up into a bunch of different little pieces. How many pieces there are is going to be equal to the number m, which is in some sense the number of fundamental periods that are represented in the solution, times P1, times, P1, which is just that numerator over there. In the previous example, we had m equals 1 and p is equal to 2/3. So there were, there's going to be one more than that. All right. So that's the main point here. We can split our solution up into segments, and then those segments satisfy boundary value problems. And those boundary value problems are ODE boundary value problems, which is nice. And this delay shift here that I've sort of introduced at the bottom, it represents how much, in some sense, how to move, how the derivative of one segment is related to another segment. So in the previous one, it was like a shift forward by one, but it could be something more complicated. So we've done this for delay differential equations, and now we have to put these jumps in. So we can do it for impulsive delay DEs. So without going into too much detail, the idea is I write down the same sort of representation of my periodic solution as by representing it on one period in the same way as I do before. I assume that I have some segments, these ZKQs, that are differentiable on this sort of interval from 0 to 1 over P2, where, again, the analogy going back to the previous example was earlier we had 0 to 1/2. So just however far we have to split up our periodic solution in order to maintain a nice amount of regularity on those segments, maintaining the requirement that those segments are all of the same length. Since this thing is going to have a jump in its state whenever time is a multiple of p, the natural length of that segment is just 1 divided by the denominator of the fundamental period. So the situation is exactly the same. The only difference here is that the boundary conditions are going to be different because we have to deal with the fact that, for example, at time p, there's going to be a jump. At time 2 times p, there's going to be a jump up until m times p, whatever those are. So I won't write down the actual derivation of the boundary condition because it's a little bit, well, it can be a bit awkward the first time you see it because you have to be careful with all these left limits and, you know, especially the way I've represented things here to make things explicit. The indices get a bit confusing, but the main point is that this can be done. And you'll notice that there's the only real main difference here in the boundary condition is that at some specific indices, the boundary condition changes from just relating these segments at the endpoints 0 and 1 over P2 to something very much like that, but with something involving the jump condition or the jump function G. So ultimately, yeah, that's the main point. The main point is that this idea of transforming a delay differential equation and the problem of periodic solutions into a boundary value problem can be done again for impulsive delay differential equations. It does still work. So what I'm going to do now is do a little bit of a setup to make things nicer later. I'm going to be eventually using Chebyshev series to represent my solutions. So I'm going to do the standard thing, which is to shift the domain of each of the segments from 0 to 1 over P2 into the interval -1 to 1. So if you've seen this done before, this is yeah, pretty standard stuff. There's not really much to say here. And I'm imposing this sort of like cyclic condition on one of the indices, just so that I can eliminate one of these 3 cases in the boundary condition. So now my cases for the boundary condition just amount to the situation where I don't have an impulse to deal with, in the case where Q is not equal to P1 minus 1, and the case where there is an impulse to keep track of where Q is equal to P1 minus 1. So if I do that.
Kevin?
Yes. Yes, Jean-Philippe.
So, sorry, Kevin. I mean, it's not, I don't have a question. It's more like a technical thing. Do you have, are you using your cursor in your talk?
I'm not, no.
Okay, no, it's okay. I was wondering if sometimes you're pointing and then, okay, that's fine. I just wanted to make sure.
Yeah. Okay. You know what, maybe I can, it's possible that I can switch it so that I can. If I do this instead, can you see my cursor now?
Yes.
Okay, cool. Well, then
No,
I'll do that from now on. This
it's
is
more like there's a lot of
perfect.
formulas, and sometimes you're referring to a part, and then I wasn't sure if you meant to be using it anyway. All right.
Absolutely. That's a very good point. Thank you. I will use this little mouse hand from now on. Okay, great. So yes, yeah. So as I was saying, yes. So yeah. So I'm introducing this little cyclic condition here, mostly so that I can eliminate one of these two boundary conditions and just clean up the presentation a little bit. So now we only have two. So with this shift into interval -1 to 1 done, I can state one final result here before moving on to the rigorous numerics, which is to say that, so this first part, if f and g are analytic, then these segments, these phi k q, which are the shifted versions of my old segments to the interval -1 to 1, those are also analytic. Technically, I don't require G to be analytic for this to be true, but I mean, it's sort of written there just for symmetry, and because we will kind of need it later. So the summary of this whole story is that if f and g are analytic, then every periodic solution of my impulsive delay dE, if for a period being the multiple of a fundamental period, which is rational, it is going to uniquely determine an analytic solution of this boundary value problem, BVP1, BVP2 at the very top. So that's good. That means that we have a hope of solving it because everything is nice and analytic now, which means I can, well, I can do the natural thing when I have a boundary value problem that I want to solve. I can represent everything in terms of Chebyshev series. So just a reminder, these t subscript n are what are called the Chebyshev polynomials of the first kind. They satisfy a particular recursive formula, and they're used a lot in approximation theory. Their derivatives satisfy some nice relationships. Their integrals satisfy some nice relationships. What we do here is since our functions phi k q are analytic themselves, because we're assuming that previous situation of the lemma, we can expand them as Chebyshev series as done right here. So now what I'm going to do is I'm going to think of some kind of abstract object. I'm going to call it A, which is some big tensor of all of my Chebyshev coefficients. So these things are going to have three indices. They're going to have indices k, q, and n. K and q relate to, in some sense, which solution segment we are talking to. These k and q range between 0 and m, and from 0 to p1 minus 1. And the n is indexed by the natural numbers. And again, since these functions phi are analytic, I know that there's going to be some nu such that this norm here, so defined, is finite. So now what I'm going to do is I'm going to say that these a subscript kq's are in this space that I call L nu 1. And I'm going to write that the entire element A, which is just like each of those, sort of the product of all of those segments together, that is an element of L nu 1 to the m times p1. The specific choice of norm on the right-hand side of this definition, just take it to be any norm on the complex numbers to the power d. So any norm on complex d-dimensional space is fine. So I can expand phi, as I've done before. And in order to make this transformation to sequence space complete, I need to do the same thing with f. So suffice to say that this can be done. And if f is a polynomial, then this basically transforms f into a polynomial where multiplication is like convolution. And if f is not polynomial, then if it's analytic, then ideally what we would do is we would do some transformations first to polynomialize the vector field, do some automatic differentiation, and make it polynomial. That might introduce extra boundary conditions we have to worry about, but suffice it to say, if it's not polynomial, then that can be done. So that handles the ordinary differential equation, and we now have to do the same kind of thing to the boundary condition. So this boundary condition here, it's specified in terms of the values of phi at -1 and +1, as well as the function g evaluated at a few different segments at +1 and -1. So to do this, we use the fact that the Chebyshev polynomials have some fairly nice properties. They evaluate to 1 at x equals 1, and they evaluate to -1 to the n at x equals -1, which allows us to represent the left side and the right-hand side. This should say at phi at -1. Oh, sorry about that. Let's go back. And we can similarly expand the function g in terms of Chebyshev series as well. And once again, this will turn g into this sort of polynomial in terms of convolutions. So again, the next slide is a big ugly formula slide. It's not terribly important in terms of what is written in the middle. The main idea is that once we've done that computation in the previous two slides, we then replace all of the phi's in our differential equation and our boundary conditions with the Chebyshev representations. And then we take all of those equations we get, we rearrange them a little bit. We basically push them all to one side of a big equals 0 sign. And at the end of the day, we get this big map, F, whose zeros are essentially, well, by construction and by what we know about the functions phi, they are uniquely associated to periodic solutions. If we just invert this entire transformation. So our problem of finding periodic solutions is now equivalent to finding a 0 in this m times p fold product space of L nu 1 sequences. And now everything is standard. Now everything is very normal. So I'll put up the obligatory theorem that has been put up in these talks many times, and I'll just briefly go over how it works. So the theorem, which is sometimes called the radii polynomial approach, says that if I have an approximate 0 in some Banach space X, I have a map from some Banach space X into Y, and I suppose it's C1. And if I can find these bounded linear operators A dagger and A, one of them being injective, and I can find a bunch of constants such that all these inequalities are satisfied, then I can find a ball of some specified radius around my approximate 0 that definitely does contain an actual 0 of my map. I won't talk too much about how exactly this theorem works because, again, this is something that's been talked about before. The main idea is that you take the Newton-Kantorovich theorem, you take the Newton operator, and essentially, at the end of the day, if all of these conditions are satisfied, then the Newton operator is contracted on a particular ball, and it's that ball down there at the very bottom. This ball at radius r0 for any positive r0 such that the polynomial, the radii polynomial, is negative. And I mean, I really shouldn't be calling this talk, rigorous computation of periodic solutions, because I really should just be talking about, it should be called something like, how to set up rigorous computations for delayed differential equations, because I'm not going to be talking too much about the numerics, actually. It's really just all set up. But there'll just be one slide here just saying how to set these things up for this particular problem. Again, this is pretty standard stuff for a lot of you, so not too much time. Basically, we take the domain of our map F, which is this, which is that product space of many copies of L nu 1. We truncate the number of modes in the domain. Then we truncate the output of the map. That's going to define a finite dimensional object. that acts on a finite dimensional space, which means I can represent it in the computer and do Newton's method to find an approximate zero. And then I can define my A dagger and my A based on the Jacobian of that finite dimensional map at my candidate zero and its numerical inverse. And then I can define the A dagger and A using those objects plus information related to how the tail of that operator should behave in order to make it bounded. And with that construction, yeah, basically I have the results that I need. And I can explicitly characterize the codomain Y if I want to, but it's not really necessary to make this work. So yeah, that's how periodic solutions are going to work. I will do an example later on. I won't actually compute the bounds or anything like that because again, that's standard stuff for a lot of you here. But I can talk about the details, I guess, if anybody has questions later. So right now, we've talked about periodic solutions, and now I want to talk about, you know, how to linearize. Well, if you linearize at a periodic solution, what can you do? So, right. So again, suppose I have a periodic solution. Maybe I have error bounds related to the higher order modes. Maybe I don't. Maybe it's something completely explicit that I have on paper. If I want to know whether this object is stable, if I want to know, you know, for example, the dimension of its unstable manifold or stable center manifold or something like that, I need to do a linearization. So that will give me, at the end of the day, a system of this form right here. The coefficients of A and B, these things could be time varying, and in fact, they will be if I'm linearizing at a periodic solution. And they will have the same period as the periodic solution that I started with. And if this is coming from an impulsive delay differential equation, then there will be a relationship between the period of the forcing, which is P, and here the forcing is like the impulse effect, and also the forcing that is coming from A and B. So some baseline hypotheses I will have to assume, just because, well, I'm going to assume that P and Q are natural numbers. This is analogous to the assumption I made earlier, where earlier I had rescaled the delay to be equal to 1, and then I said that the period should be rational. Really, this is just another way of saying that. You could pretend that I've scaled the delay to be this natural number Q, and then I require the delay to be a natural number as well. I'm also going to be requiring 1 to be less than or equal to P less than or equal to Q. The P less than or equal to Q part, that is something that can be relaxed, and if anybody's interested, I can talk about that later. But for the time being, I'm going to assume this. So basically, period is smaller than delay, or smaller than or equal to delay. That's the situation we're working with right now. And the other assumption is that I'm going to assume that the matrices A and B that define the vector field, they can be represented as Chebyshev series, specifically piecewise Chebyshev series. So this is, again, very much like what I did last time. I'm assuming that if I split up my interval in which my function is periodic into segments of the same width, in some sense naturally defined by where the impulses are going to happen, I'm assuming that everything can be represented as Chebyshev. So if I do this, even if I don't do this, I can define this sort of natural analog of like my Jacobian from ODEs. I can define this operator M called the monodromy operator that encodes, it's kind of like the period map or the Poincaré map. And what it does is it contains all the information about stability of x equal to 0, the dimension of unstable fiber bundles, everything like this. And what I've written here, this RCR, it's a notation that I was using during my PhD that I've kind of stuck with. It stands for right continuous regulated. It means continuous from the right with limits from the left. So this is the sort of natural phase space for these types of discontinuous dynamical systems. Ultimately, what I'm interested in is the eigenvalues of this operator M, which takes my initial condition and flows forward p time units, and then gives me my output. Because again, this tells me a lot about x equals 0. So what I want to do is represent M, and then I want to realize its eigenfunctions as being part of a nice space. I want to represent the operator on that nice space, and then I want to use rigorous numerics to do computation. So now we get to do some more pictures. So one somewhat nice thing is that an eigenfunction of that operator can only be discontinuous at an integer. So in particular, if I draw a picture of a potential eigenfunction right here at the top, so this one, for example, the delay is 2. So I only need to represent it on the interval -2 to 0. And since discontinuities can only happen at the integers, it is natural to split it up into, in this case, 3 objects. The part of the solution from -2 to -1, which is this object over here. The part of the solution from -1 to 0, which is this object over here. And then we have to take this other point over there and treat it as the last part. And the reason I want to do that is because, well, I want to represent this object in a product space in such a way that each sort of factor is continuous or well-behaved. So I need to sort of take this point away and, give it its own special box. So if I do this, then I can uniquely represent eigenfunctions of this operator as elements of this space. I've written this superscript C0 here, and I should really have written somewhere else what exactly I mean by that. What I mean in this case is continuous on that interval, and the limit as x goes to 0 from the left exists. So I can't have any crazy wiggly stuff. I can't have anything like sine 1 over x in there. That would be bad. But that is okay because those types of objects aren't in the phase space of the operator itself, so it doesn't matter. So this operator M should be taking my initial condition phi and giving me the solution 1 full time unit forward, and it should be then mapping it into the phase space. So I should take a function phi and get a new function. I'm going to call it M of phi. And this thing should be defined for theta between -2 to 0. So I'm going to pretend that this thing M generates a solution Y. And if I do that, then sort of informally, I have a picture that looks something like this. So I have my entire initial condition defined from -2 to 0. And then I have to flow forward 1 time unit if my period is equal to 1. So then something happens along this pink, I guess it's magenta dashed line here. And that is Y restricted to 0, 1. And then I have a jump that happens because time is an integer. And I get, I get a new point over here. So informally, I can think of this operator M taking my initial condition phi and spitting out 3 things. Something called Y at 1. This pink function segment here shifted back to the interval -1 to 0. And something else, which I'm calling Y0, which is going to correspond to the blue segment. Really, what this M does should be taking this entire box from -2 to 0 and outputting the entire box that is from -1 to +1 and then shifting it back so that its domain is -2 to 0. That's what it should be doing. So informally, that is when I'm going to write that this operator does. So what we can do now is use method of steps. And I've skipped a couple of details here because it's not, you have to do a couple of changes of variables to make this work out so nicely. But at the end of the day, we do method of steps and we can get these formulas for Y1 at theta and Y at 1. So what should be, not too hard to follow though, is that the value of Y at 1 is going to be determined by an impulse effect. So it's going to be because of the way my delta x is defined, it's the change at time t1 has to be c1 times the left limit plus c2 at time t minus 2. So that's exactly what I have right here. And if I calculate that left limit using the value, using y1 at theta, which I computed earlier, I can write it like this. And what I'm going to do now is highlight, using green and blue, exactly which parts are from the input of the operator m and which are the outputs. So the inputs are all in blue, the outputs are all in green. So what I'm trying to do is I'm trying to represent the green stuff in terms of the blue stuff. Because if I can do that, then I can actually write down my monodromy operator in terms of nice integral operators. So doing that, I can define this integral operator L subscript y, and I can use that as well as this evaluation functional at 0 to, in some sense, write down like a matrix equation almost for my outputs and inputs of my monodromy operator M, which is really good because if I now, collect all of those terms together, I bring everything over to one side, I sort of factor a bunch of things. I can identify two operators. The one on the left here, multiplying onto m phi, I'm going to call this I minus w. W is sort of the, well, it's all this other junk that isn't the identity, I guess. And then I have this operator E over here. The E, I'm calling it E because it's sort of like an explicit part. The W is implicit, sort of, because I'm going to have to invert it later on. But anyway, E is very explicit. That's all I really have. That's all I've got. And what you can show is that this operator I minus W, it's a Banach space isomorphism. This can be proven in full generality. Again, C0, the lift limits at 0 have to exist. That's the only caveat. In order to make it a Banach space, I require that. And the point is that, like before, this can be done in full generality. If P is less than or equal to Q, I can build these operators M, I can build E, I can build W, and I have this factorization. So I can write everything in terms of integral operators and evaluation functionals and matrix multiplications. So what I'm going to do now is start to move towards Chebyshev series. So to do that, I'm going to identify a particular subspace of the domain of that operator. And it's basically going to be those functions that can be represented as Chebyshev series with L nu 1 coefficients. So the setup here is very much the same as I did before. And what one can show is that if I have those baseline assumptions satisfied, and additionally, I assume that the sequence matrix coefficients of my expansions of the expansions of A and B, if I assume that those Chebyshev expansions have coefficients that are themselves also in L nu 1, then every eigenfunction of M has to be in this space. So it is perfectly legitimate to represent M on that space and compute eigenfunctions there and compute eigenvalues of that restricted operator on that space. So I'm going to mostly skip over the details of this slide, but the main point is that with these integral operators, we can represent them on the space of Chebyshev sequences with L nu 1 norm, bounded L nu 1 norm, in terms of convolutions. So instead of working on this abstract space of functions that have representations as Chebyshev series, we can once again move directly into sequence space and represent the operator on that space instead. So with that part done, I can very quickly run over the rigorous numerics because the setup is basically finished. So I am assuming that the coefficients of my delay differential equation, they might only be known up to some particular number of modes. That's going to be true if this is coming from another computer-assisted proof of a periodic solution, for example. So the first thing I want to do is I want to formally truncate the operator M itself by replacing my full expansion from a matrix coefficients A and B with a mode N1 mode truncation, whatever that happens to be. And that's straightforward enough. I basically just rebuild I rebuild the operators E and W with those truncated expansions instead of the full ones. That's straightforward enough. What I need to do next is I want to be able to represent M as a matrix. So to represent M as a matrix, I'm going to do the exact same thing that I did when I was looking at periodic solutions, which is I'm going to basically truncate the input of my operators W and E to some finite number of modes, N2. I'm then going to truncate the outputs. And then I'm going to rebuild that operator in the exact same way as I did before, as this, this product of the identity minus the inverse identity minus W inverted times E. And yeah, one can show that in fact, yes, this operator here, I minus W, is invertible. And by construction, if you do this, then the monodromy operator, the discretized operator, M subscript N1, N2, will be compact and have finite dimensional range. So with that, we have this, this theorem, which I partially borrowed from Jean-Philippe and Jay, which basically tells you how you can compute generalized Morse indices using a homotopy argument. So the way this theorem is proven is you sort of define a homotopy between M, the actual operator, and the discretized operator, and show that as you flow along that homotopy, you don't have any eigenvalues that cross the unit circle, or that cross a circle of radius r in the complex plane. The point here is that for doing things on a computer, the constants C2 and C3 are explicitly computable. And as for C1, this thing at the bottom, we can compute that using interval arithmetic as well, by sort of computing a mesh over theta and computing these objects, this norm explicitly. So that's been a lot of, at times, very, very heavy, finicky math. Now we can do some applications and do some pictures and see what all this stuff can do. So the Hutchinson equation, that's the equation at the top. It also called the delayed logistic equation. All the parameters here are k, tau, capital T. Those are all positive numbers. K represents the carrying capacity. In the example I do later, it's going to be equal to 1. R is a growth rate. Tau is a delay. And beta here is a number that, since this is the impulsive, or the pulse harvested Hutchinson equation, here beta is a number that represents, after the impulse happens, how much of the species X is left over in proportion. So if beta is equal to 1, for example, then the impulse does nothing. And we just have the Hutchinson equation, which, as I'm sure a lot of you that do delayed differential equations know, has periodic solutions if r times tau is bigger than pi over 2. And then we have a few other properties of periodic solutions. And the sort of natural question we want to answer is, between what I'm claiming is a bifurcation point at e to the minus r tau and 1, what exactly happens? So with some example parameters, mostly chosen for illustrative purposes, but there are more of them in the paper, what we can prove is this. There is a branch of periodic solutions that comes out of the transcritical bifurcation at this parameter beta star, which is e to the minus 1. As beta increases from that number to 1, this branch is connected and it is smooth, and it satisfies at beta equal to 1, so where the impulse does nothing, it corresponds to the steady state x equal to 1. And this branch has no folds. So in terms of how this is actually proven, it's computer assisted, and we do it sort of in two pieces. First, we compute the branch from 1 down to some number beta, which is basically determined by when the proof fails. Because since we have a transcritical bifurcation, we have non-isolation near beta star. We're going to have two distinct solutions. Near beta star, what we do is we do a desingularization. We introduce a quasi-amplitude parameter, and we study that blowed up system instead and use the same kind of continuation argument, rigorous continuation, which was not talked about before, but I think other people have talked about it in previous seminars. And then we basically use the outputs of the Rayleigh polynomial to connect the branches and also show that this branch actually does cross through 0 and crosses through the transcritical bifurcation point. So that's the main result. And so now I can show you a very painful to look at picture, mostly chosen because of its high contrast, so that when I switched to black and white mode, I could still tell which colors are which. So what you're looking at here in the green colors is the part that we proved without the desingularization, without the blow up. And the part in pink and purple is the part that we had to prove with the blow up. And in terms of the coloring, so I have dark green and dark purple and light purple because since the delay is 5/2, once I rescale time to make the delay equal to 1, it becomes 2/5, which means I need 2 copies of L nu 1. So there's 2 sort of sheets that I have to prove. So that's great. That looks like something. I can't really tell that it's a periodic solution though. So Kevin, can you show me that it's a periodic solution? Well, here's what it looks like if you stack them up for multiple periods. So when beta is equal to 1, the value of the function is identically equal to 1, so it's continuous. Beta is equal to 0, it's identically equal to 0, as indicated by the colors. So my periodic solution is indeed continuous, and it's 0. And everywhere in between, it's discontinuous. And it has a discontinuity at the integer time 1, as it should. So great, we've computed a periodic solution, we've computed a branch of periodic solutions, and in particular, we've proven that it actually is there, which is great. And it has no faults. What we can do now is we can use our monodromy operator discretization and compute some Floquet multipliers. So to emphasize, when beta is equal to 1, we are indeed computing an unstable object. When beta is equal to 1, since 5/2 is bigger than pi/2, the actual attractor is most likely going to be that periodic orbit that comes from the Hopf bifurcation in Wright's equation or Hutchinson equation. So we are computing an unstable object. When beta decreases, we get crossing through spectral radius equal to 1, and I don't have a proof for this, but I'm telling you right now it's a Neymark-Sacker bifurcation. We further decrease, that orbit becomes more and more stable, and eventually it's going to lose stability through that transcritical bifurcation that I mentioned at parameter beta equal to e to the -1. So these are all, this is all proven at the discrete points on the branch. Actually, I shouldn't say proven. This is just the discretization. None of these are proven. This was all done yesterday just for the talk. Didn't run any proofs for this particular section. The other part was proven though, because that runs in like a few seconds. This would take way longer. So just some closing remarks. So we can compute periodic solutions of impulsive delay dE by converting the problem into a boundary value problem. We can then take that boundary value problem and, as is typical with boundary value problems, we can solve them by transitioning to sequence space, specifically Chebyshev space. And then we can use the computer to find zeros and prove their existence. We can do that for branches of zeros as well, as I did in that example over there. If we want to know stability of that orbit or compute unstable the dimension of the unstable manifold or something like that, we can represent that operator on a particular product space. And then we can use the computer to count the number of Floquet multipliers outside of the ball. So we can do stability, we can do lots of stuff. And finally, just as an example, we applied that to the pulse-harvested Hutchinson equation. I showed you a couple of pictures. Some of them kind of hurt to look at, but yeah, that's basically it. So I will again mention about half of this presentation is based on something that Gabrielle and I started working on in May of last year at the workshop that was organized by the CRM. So we've kind of come full circle here. This started with something coming out of the CRM, and it's now presented here at the CRM camp. So it's been great to talk to you all, and thanks for listening. Happy to answer any questions.
Thank you very much, Kevin.
Thank you.
Are there any questions, comments, remarks?
Kevin, you said you have this Neimark-Sacker bifurcation?
Yeah.
Have you done simulations? Is there a torus that comes out of that? Or?
Yeah. So my, yeah. So I said I claim that there is, and I haven't done simulations yet. What I can tell you, just based on what I do know, if I were to perturb parameters so that I was at the Hoff bifurcation in the system without the impulses, what will happen is if I sort of, oh, I'm getting a little bit of echoing. Ooh, that's distracting. Okay. So basically Hoff bifurcations and delay DEs, once you sort of, if you perturb away from that using an impulse effect, what will happen is that, so you would get the Hoff bifurcation, but actually you then get for free what would be an invariant torus. But since the torus, it can't sort of persist because of the discontinuity, it actually gets broken, and then you get a cylinder. So yeah, you will, I haven't done simulations, but I promise, I'm actually 100% confident in this. You will get a, you won't get a torus, you'll get a cylinder. Yeah.
What do you mean a cylinder exactly?
So if you do a three-dimensional, so if you, for example, plot your, if you plot your solution in like variables x at t minus something else, xt minus something else to embed it in 3D, instead of observing something that looks like a torus, you will observe something that looks like a cylinder, which in some sense,
but if you
like,
identify,
exactly,
yeah, okay.
Exactly. If you identify it up to the boundary, then yeah, it's a torus.
Gotcha. Thank you.
Yeah.
Other questions?
I have a question concerning the proof of your computer-assisted proof of periodic solutions.
Yes.
So actually, that has, from my point of view, that has two clearly distinct parts. Namely, the first part is you transform it into the boundary value problem for that system.
Yeah.
And then you treat that boundary value problem by computer-assisted means.
Yes.
But so my question is, so or my conjecture is that you could do that by any method for boundary value problems. So that means you don't need to take Chebyshev series. You don't need to take series expansions at all. You could also treat this boundary value problem by other means, for example, in Sobolev spaces, and then you have that would amount to much weaker assumptions on the nonlinearity F. So you're assuming analyticity of F and G to be able to do that series expansion.
Yes.
But I think if you choose another boundary value problem solver, that's not really necessary. Is that right?
That is certainly quite, I believe you, that's certainly quite likely. My reason for assuming analyticity and working with Chebyshev is mostly because, I mean, as Jean-Philippe suggested, this is all very new to me. Sure. So I was working...
That's your surrounding neighborhood, so to say.
Yeah.
Yes, but at the same time, Chebyshev series, they work for absolutely continuous functions. So in fact, you could have C1, you could have only C2 functions. So in fact, they're much more versatile than Taylor series. So you could have very low regularity and you could still use them. You would just have to wait. You would just have to change from an analytic weight to a CK weight, but you could still have a Banach algebra with algebraic decay. So that's not a problem, in fact.
Yeah, but at least you need analyticity assumption on F and G, right?
It would depend on how that composition would work out. So, I mean, I don't, at this stage, I don't think I'm fully qualified to answer exactly how that would pan out. But I'm open to looking into it.
Yeah, definitely the algebra would be easier. I mean, it's more natural with the analyticity, but yeah, it's a good point. But in terms of the actual functions themselves, if the solutions were low regular, I mean, had only few degrees of regularity, then Chebyshev would be fine.
So I'm not, so this, for the solution, I completely agree. But the data, so to say, the nonlinearity, that would be a problem if that's less smooth. And at least that, so I'm not advertising other methods. I'm just asking if other methods, if I'm correct in assuming that these two parts of the solution. Right? So the first part of this transformation into a system, this is of course what should be done. This is quite natural and is maybe in some sense the only way you can do it. But then you could go also for other choices of solving the boundary.
Absolutely, yes.
Thank you.
Thank you, Michael.
Other questions? Comments? Yeah.
Okay, maybe two questions. So first, I'm wondering about the regularity about the solution. You see, you mentioned that the solution is a piecewise analytical function. So wondering about the regularity at the connecting point.
Yes, at the connecting point. So I should specify the, so let me actually go back to the slide that you're referring to. Yes. Yes, this. I assume you're referring to this part. Yeah, so if f and g are analytic, then yeah, I have a uniquely determined analytic solution of the boundary value problem. So the important thing to remember is that the boundary value problem itself is sort of agnostic to the fact that I am solving a discontinuous problem. So the boundary value problem itself, having an analytic solution, is entirely due to the coefficients, f and g being themselves analytic. And that's, I think that goes back to like Cauchy-Kovalevskaya theorem. That is, I mean, that's just, that's basic ODEs. How that's actually resolved when I want to think of this as being a solution of a discontinuous problem is because at some point here, I make this identification where I continuously extend these segments, which might be discontinuous at their right-hand boundaries. I continuously extend them to the boundary. So once I make this change, I am almost, at this point, I'm no longer really working with a discontinuous problem. This is the sort of minor, like sort of subtle step where that potential lack of regularity is dealt with. Not sure if that will completely answer your question.
But your final solutions, they can have piecewise jumps, yes?
Yes.
Okay,
Yeah.
so globally, it's like a piecewise analytic, but globally it says jump discontinuity.
Yes,
yeah, it is going to be, yeah. It's globally analytical, but it does have jump discontinuities.
Well, yeah. Physical meaning, because in real world, so I think the solution should at least be continuous, and maybe this delayed this partial differential equation is some model from the physical phenomenon. And so how about the physical meaning if it is not so smooth and at the connecting point?
So,
well, like the harvesting is a good example, right?
Yeah.
One morning you harvest and now there's just 80% less crops in the field than there were the day before that or something.
Yeah. Yeah, so I mean, these models, they're sort of like an idealization of if there's some kind of shock to the system that happens very quickly relative to transient dynamics. you could model them as being continuous events instead. And that will give you a sort of like a piecewise smooth system. And in some kind of, in an appropriate scaling limit, you get these types of discontinuous problems. But that's an entirely different topic.
Yeah, but harvesting naturally leads to discontinuous.
Yeah.
So let's say it is very realistic, the discontinuity in that case.
And I think also that has nothing to do with the delay differential equation. You could do that also for an ODE.
Yeah, absolutely.
Without delay. So that is this discontinuities I think are quite natural.
Yeah, I mean the theory for impulsive differential equations. This was all, I mean the sort of theoretical background, like where you don't work with distributions and delta functionals and stuff. This was all developed in like the early 80s. Yeah, of course, it started without delays.
Okay, I see. At least as mentioned by Plum. So delay is not the essential.
Oh, absolutely not. Yeah. No, we could do this for ODEs. People have looked at this for PDEs. Yeah.
Okay. My second question, so about the relative polynomial approach, maybe on the 19th page. So I'm wondering, so this method is just designed for the Chebyshev system or a more general framework. So maybe could you give some comment about the such theorem?
Yeah, so I mean, the theorem as stated here is fully general. The only requirement is that X and Y are Banach spaces. So as Michael was suggesting, if I did some kind of expansion in terms of a different basis, and I different from Chebyshev, and I set up my sequence. I had some kind of other basis, and I worked with a different Banach space, maybe with a different norm. And if I set this up correctly, then I could for sure apply this approach there as well.
Particular also for Sobolev spaces. That was my basis.
Yes, Sobolev spaces. Yeah.
Yeah, and as Kevin mentioned, this is basically Newton-Kantorovich with Newton and an approximate inverse. So to some extent, it is as general as you want. This is very general theorem.
Okay, I see. But I know little about it. so okay, thank you for your comment.
Thanks for your questions.
Okay, other questions or comments?
I have another question. I'm not sure if that's stupid. So you see, concerning these jumps, you could also from the beginning, you could consider any function, maybe a piecewise linear function, which just has these jumps, and then subtract that from the solution you're looking for. So, and then you, in this transformed system, then you are looking for continuous solutions. You know what I mean?
Yeah.
I'm not sure if that would help.
Yeah, so yeah, so I suppose you could. That would introduce some. So I guess, yeah, you could do that. I guess then your vector field would then become piecewise continuous in some sense.
It would be continuous and piecewise smooth.
Yeah, it would be continuous and it would be it would be piecewise. I'm not sure if it would be.
Of course, you would get discontinuities in the differential equation because by subtraction of that discontinuous function, you get discontinuous parts in the differential equation.
Yes.
So the whole point is. Is it useful to have continuous solutions but discontinuous coefficients, so to say, or is it doesn't that help much? That's what I'm not quite sure about.
Okay. Yeah, I haven't thought about that too much. My intuition is that if you did something like that, then as you said, yes, you would introduce some piecewise. You would introduce some discontinuities in the vector field. One thing, which is not too big of a deal. But you would also introduce some additional path dependence. So you know how what I've done here is I get those ODEs that are only cyclically chained to one other part of the solution. I suspect if you did it this way, then the more you propagate forward in time, the more I think you'd have to take into account the entire history of the periodic solution at every point. I'm not entirely sure where I'm getting to this, but I think that might introduce some extra functional dependence as well as the extra discontinuities in the vector field. But I mean, it could help. I guess it depends on if there's a more efficient way to set up the problem after that transformation is done.
Yeah, exactly. That's not clear.
Yeah. Yeah, that's a good point. That's something that, yeah, might be more appropriate for other situations, especially. Yeah.
Okay. Other questions, comments? So in that case, would that lead to some Filipov type system or not really?
Oh yeah, absolutely. I mean, I think you've done something with that.
Yes.
And
yeah,
I
but
mean,
in that case, this is like, it's more global, right? There's like a switching manifold, which kind of determines in phase space where the dynamics changes, but it doesn't look like here it would be very appropriate.
So, I mean, yes, you would need to append an additional condition that keeps track of, like you almost have to, I mean, here I'm looking at a periodic solution, but my phase condition is almost like the boundary conditions. There, if you wanted to do something with Filipov, then in some sense, your phase conditions almost become the interface conditions when your solution crosses a switching manifold. So, I mean, for sure, the same kind of idea works there.
Okay.
Yeah. Really, any kind of like piecewise smooth setup is amenable to this kind of segmented approach.
Yeah, because you see, Michael, so I've worked on some of these Filipov problems at some point, and if you think about a piecewise smooth dynamical system, which now it's not analytic, it's not even, you know, it's piecewise smooth. So on one side, so there are these manifolds which we call the switching manifolds, which split the phase space. So on each of these sides, then the vector fields are analytic. So then you can kind of solve with Chebyshev some segments, and when you change from one side of a switching manifold to the other, then there is a discontinuity there. But you can still kind of apply the same idea as Kevin is saying, like you kind of solve piecewise analytic segments. So something like this can be applied as well. So even though if the vector field is really low regular, then if you can kind of compartmentalize it so that in blocks it is kind of very smooth, then these kind of methods can still be applied. Yeah.
Kevin, I had just one more question. You remarked that your setup was for period shorter than the delay.
Yeah.
You said there was a fix for period longer than the delay. Is that too much to go into, or is it kind of?
So, yeah, where did I write that down? I wrote that down at the very beginning of this section. Yes. So there, I can say two things. First, the restriction doesn't matter if you're not interested in computer-assisted proof.
Okay.
It's
well,
not a.
Assume I was.
Yeah. Assume you are. Assume you are. Then the C1, C2, the C2 and C3 bounds in this proof here. So you need another type of bound, which controls a different kind of error, and they become horrible. Like,
so this is just way for more stability. This is more for the stability than the proof of the existence of the periodic orbit.
Oh yeah, this is just for the stability stuff. For the periodic orbit, there's no restrictions at all. Just that the period, the period and the delay are commensurate. Yeah. If they're non-commensurate, then things get kind of weird because, as I said before, the solutions can become very irregular. I mean, there's still going to be Lipschitz continuous, but that's the best kind of regularity that you can hope for.
And you're saying for the stability, looking at this, it looks insurmountable in the.
It's not insurmountable. I was initially considering doing it, and I sort of had put together like I have a tactic to do it. In that paper at JDD, I sort of talk in the conclusion how you can do it, but the bounds will take up more than a page.
So
right
it's
now they don't.
More pen and paper work.
It's lots of pen and paper work. Yeah.
But maybe for the computer, not much more work.
Yeah, for the computer, it wouldn't be that much more work. It does, so one thing I didn't talk too much about in the Hutchinson equation, for example. So here, okay. So if you look at the ratio of the fundamental period t divided by the delay tau, the difficulty of the proof scales with the denominator. So if you have large denominators, then your proof gets harder. There is going to be a similar condition for the stability related to essentially, it's going to be something about the denominator of the period divided by the delay or the other one. So there are some situations in which it could be very hard for the computer to do. But yeah, I haven't looked at it too much.
Okay, thanks a lot. Thanks a lot.
Okay. I guess it's 11:20 here. It must be pretty late in Japan. In Europe, it's also getting a bit late. So I guess we'll stop here. Well, thanks a lot, Kevin. I mean, thanks for giving a very detailed and entertaining talk.